Hi guys, and welcome to the second part of this week. We're in week 4. We have quite a few things that are interesting. First of all, we really need to finish that part of this week that we didn't finish last time. We're still talking about the solar system. We're trying to understand basically how the solar system works. And this part right now, we already looked at the properties, what it's made up of, and things like that. Now we're going to be talking about the history, if you wish, how the solar system came to be, and also how it evolved and how we came to know all of these things. Okay, at some point down the road, we'll be studying the sun, and we'll see actually how the solar system will end, basically at the end of the day. At least the sun, how it's going to go. Okay. Because some of the planets that are far away from the sun, they will probably survive that, but the planets that are the inner planets, most likely they will not survive the end of the sun. So this is basically what we'll need to be covering. Before I do that, before we dive into the topic, there is something of extreme importance that I really want to emphasize on its importance at this point, because you guys know that we have an exam midterm next Wednesday, a week from today. Today is September 28th. On October 5th, we will have our midterm, okay? You have the review already on campus. You should have plenty of time to do your review. There is no really reasons why you cannot do it. If you're working during weekdays, or you have other classes, or you're a high school student and you have classes that you need to basically take care of or attend, you still have time during the weekend. So there is plenty of time for you guys to do the review. The review actually will close on Tuesday night, October 4th, okay, in the late at night, around midnight. It's not going to be available. So by then, the assumption is you went through the review. Please go through the materials. Everything we covered up to today is included in the midterm, okay? And that is unit 35. So everything is going to be covered in there. That's why the review actually was not made available until today. So today you should be able to find the review, and you can start it so that you can complete everything. The review by itself is actually a graded assignment. So meaning you're going to get points for doing the actual review. Granted that Canvas will give you points based on the correct answers that you're going to be doing, but because there are a lot, and the purpose of the review is just to help you prepare for the actual exam. So in a sense that you're not going to be penalized for not knowing these things or not answering them correctly, because the purpose of this whole review is just to prepare the actual midterm. So you're going to get a full grade, that's a promise, and it's already posted in there in the review, if you start the review and actually submit the review. No matter what Canvas will give you, you're going to get full credit. The only way you're not going to get any credit whatsoever if you don't do the review, okay? The grade of the review is going to be part of your participation in the class, because you did everything you're supposed to be doing to pass the class, to do well in the class. So you're going to be rewarded for that by doing actually, having this part of the grade to go towards your participation. So again, it's very, very important that you guys do the review. It is very important that you take it seriously and dedicate the time to it, okay? Fully engage in it. Go through the units that are covered again, units 5 and 6, 7, 8, and 9, and 10, 11, and 12. Those are from 5 to 12. And then we jump to unit 34 and 35, okay? So those are the topics that are covered in the exam, and those are the topics that are covered in the review. So please do that review. There is nothing you're going to lose from doing that. As a matter of fact, you only gain, and you gain two things. As I was talking about, you gain the grade for participation, full grade, no matter what you actually score in. And then the other advantage that you're going to gain, and it's a big deal actually, honestly, is to prepare well for your midterm, because midterms and exams, they are the highest things weighted, the highly weighted items toward your overall grade. That's why you're strongly urged to do it for, like I said, two reasons: to receive benefit from it in terms of your grade, and to receive a bigger benefit, which is to prepare for your actual exam, okay? So I'm hoping that you guys are taking care of this. You're going to hear from me more, okay, down the road in terms of reminders through Canvas. So you're going to be receiving messages from me telling you that, hey, if you did the review, great. I urge you still to go and go through it to make sure that you're fully satisfied with it. If you didn't do a review, you're going to be basically reminded from me. There will be a reminder on Saturday morning. There will be another one on Sunday, especially for those who don't do it. You guys are going to hear from me more and more, okay? The actual midterm is actually going to be on Wednesday, October the 5th, okay? On that day, we will not have a live session. In other words, on Wednesday, a week from today, we will not have a live session, okay? Instead, the focus is going to be just on the midterm. So if you're having other classes, if you're working, if you're doing other things, you should have ample time to do your exam. Here's the deal. If you're working during daytime, you can still do the exam in the evening. If you have classes during daytime in the morning, you can still do it in the afternoon or in the evening. So there is enough time for you to take care of the exam. If nothing works because everything, then you still have the time allotted right now for our live session in the morning so that you guys can do the exam on that morning. So there should not be any excuse for not being able to do your review. Again, I don't make up exams. So if you miss the exam, that's it. You're going to have no credit whatsoever in it. So make sure you're ready and make sure you do your exam so that you pass the class. So that's something that is in the syllabus and you guys should be aware of it. So take care of it in the morning, take care of it in the afternoon, and no matter which way, you should be able to do that. There will be no live session because I will be basically monitoring you guys as you're taking the exam. As a matter of fact, on the same day, I have another class that is taking also a similar exam, but at different concepts. And so I will be available all day actually until what did I say? I think in the announcement, 7 p.m. After that, I will not be able to answer anything. So if you encounter a problem after 7 p.m., that's it, you're on your own. But if it happens before, I hope that you guys can, if there is a problem, let me know so that we can see what the issue is and fix it. I would strongly urge some of you, those who can, to take the exam as soon as it's available, which is 8 o'clock in the morning. That way, if there is an issue, so that we can fix it and you have enough time to basically overcome it. And that will give me a chance at least to address it with the other, your peers, basically, to make sure that your peers don't encounter the same issue. Now, by 7 p.m., as I was saying, it's too late to do anything about it. By then, most of you guys have already taken the exam, number one. Number two, well, at that point, it's too late. Even if I try to remedy this thing, if there's an issue or something, or try to help you out, it's too late. You have very limited window then to really focus on the exam and make sure you do it. So that is basically the whole plan for that, for next week. Now, a question that some of you asked, and they asked it from another class too, is what happened to the Monday sessions? Well, we have Monday. We have a class on Monday. As a matter of fact, we're starting brand new units on next week. So we still have classes on Monday. It's not canceled. The class that is basically the lab session that is canceled is that of Wednesday, but not that of Monday. Furthermore, those who are sitting in my labs, okay, and I know not all of you are required to take the lab, so it's an optional. So if you're sitting in the lab is not canceled. There will always be a lab no matter what's going on. I know a lot of you, at least those who are sitting in the lab, they're sitting on the Tuesday session. So there will be lab on Tuesday, a week from yesterday, okay, which is October 4th. So we have lab. We will never cancel labs. Something extremely terrible has to happen to me for me to miss the lab, really. And even then, I will see if I can find somebody who can come and basically cover that session. So in other words, there should never be any excuse to not have the lab. The only time when we cannot really do a lab is during the holidays, during Thanksgiving, because we have to take that week off. And then the other thing also, the finals week, we cannot do a lab. So that's the only two times where we don't have lab. Otherwise, this should never be an issue. We will have labs all the time. Those who are not sitting in the lab, those who are not taking Astronomy 125, you are not concerned by this discussion whatsoever of the lab. The only thing concerned about is the lecture sessions that we have on Mondays, Tuesdays. And in that scenario, we still have Monday session, okay? We will never really cancel anything unless there is some big something that prevents us from doing the class, okay? Now, as I mentioned, also because of the way that things are moving, you will notice that all of my exams and the midterms, they would be actually scheduled on Wednesdays, not on Mondays, just to avoid some other stuff that is happening on that day. So that is in general what's going on. I hope you guys will really take advantage of this opportunity. It's a free grade, basically. You could just open the review and submit it, even if you get 0 on it, you still get full credit for it. I wouldn't recommend that though, because that means you're not ready for the exam, which is really the purpose of the whole review. And that is going to hurt your grade big time. So you still have to do the review in order to do well in the exam. Okay. So I just wanted to take this opportunity to make sure that you guys are aware of this thing. I made sure also that this week is light in terms of assignments. Yes, there is that discussion assignment. Let me look at what we have in this week, modules. We are in week 4. Yes, we have a homework assignments and we're completing, but the homework is actually due on October 8th, which is the day after, which is really the 3 days later, okay? So again, please make sure that you do all of the assignments, especially in terms of the review. Do the homework. The homework really deals with the law of Kepler, the third law, really, mainly, okay? And what it does is it gives you the period of an object, and you're supposed to find its semi-major axis, basically how far it is from the sun. And also, or it gives you the other way around. For example, for the case of Halley's Comet, we know it takes about 76 years to go around the sun. So basically, based on that, you should be able to determine how far it can be on average, okay, from the sun, namely A. So the law we're using for the homework really that we're focused on is P squared is equal to A cubed, provided A is in astronomical units and P is in years. So if somebody asks you, you know what, I don't care about P being in years. I want it to be known in days. I want it to be known in seconds, in minutes, in whatever unit of time that you prefer. Well, compute it in years, and you know how many days are in a year, 365, and you know how many hours in a day, that's 24 hours, and you know how many minutes in an hour to 60 minutes, and you know how many seconds are in a minute, which are 60 seconds. So you keep on multiplying until you get to the desired unit that that person really requires. So the law can be very powerful and potent on its own because you use it in years. You want it in a different unit other than years, I'm going to give you that, okay? Whatever unit you want. You want it in days, all I have to do is whatever my answer is, let's say 76 years, multiply that by 365, and now you have your answer in days, okay? The same thing goes for the distance, for the A, basically, which is the semi-major axis. And we made the argument when we covered that topic that it's actually the average distance of an object around the sun. The reason why I'm saying it's an object, yes, we discussed it extensively about the planets, but this works for anything, dwarf planets or asteroids, or as long as the asteroids go around the sun, I mean, like comets or a comet or something else, okay? So as long as something is orbiting the sun, what we're talking about, it's basically how far is it on average from the sun. Now, somebody might say, you know what? How about the moon? Well, the moon, in this case, you replace the sun with the earth and the moon with any object, and then it becomes the rotation of the moon around the earth. The same thing with the 70 so moons for Jupiter. Take any moon of Jupiter, it doesn't matter, the big 5 or the big 4, I should say, and any other moon, and you're in good shape. Same thing. It's the same law, P squared equals to A cubed, except sometimes the numbers really don't make much sense, because I know Io, for example, takes only 42 hours. So it's a hassle to convert those hours into years, but thing. And the distance is, instead of expressing it in terms of the distance in terms of astronomical units, it's only a few times the diameter of Jupiter, which is 140,000 kilometers. So thousands of kilometers probably will make sense instead of hundreds of millions of kilometers. So that is basically the thing. But hey, don't focus on the exceptions. Focus on the rule, which says that p squared, p is in years, equals to a cubed, a is in astronomical units, and use that wherever you want to. It doesn't matter which object is orbiting which object. And at the end of the day, do the conversions as you like. Okay, somebody says, you know what, I don't like a to be in astronomical units. I want it to be in kilometers. Well, an astronomical unit is 150 million kilometers. So just multiply the number by kilometers. You know what, I don't like it in kilometers. I want it in miles. No big deal. Multiply by 150 million kilometers, you get it in kilometers, and divide by 1.6. And now you already have it in miles. So whatever unit you like, you can have in there. You want it in light years? No big deal. We can convert it into light years, okay? That is the time, the distance light will travel in 1 year. Light travels 300,000 kilometers in a second. In 1 minute, you multiply 300,000 by 60. You will find how long it's going to take in 1 minute, how far it's going to travel in 1 minute, I should say. You want it in an hour, you multiply the answer by 60 again to find how far the light will travel in 1 hour, and you multiply it by 24, you will find how far light travels in 1 day, and then you multiply it by 365, and you find at the end how far light will travel in 1 year. So basically, you can do conversions, but stick to the convention. That is, p squared is equal to a cubed, where p is in years, yes, and a is in astronomical units, and you're going to be safe all the time. And you want conversions, no big deal. And if you give the answer p in years and somebody wants it in days, you tell them, here it is, just it's your problem now. Unless they specifically ask it to be in days, in which case you have to convert it, okay? So this is in a nutshell something that is part of the homework for this week. But again, as I was saying in the beginning, don't bother a lot with it. Don't spend a lot of time with it at this point. Focus mainly on the review. Once you're satisfied and you know you're going to ace the midterm, then at that point, look at the homework. Because remember, the homework, one of the homework is going to be dropped anyway. So if in case you have issues with it, we can always fix it. I really don't want you to drop anything, but we can always address it later on. In terms of weight, basically, that's what I'm trying to say in here. The exam has far more weight. The midterm has far more weight than anything else that you're facing at this point. So it has to be done. Another thing that you don't forget, and you all should never forget, and that is the lunar observations. You did yours yesterday, or today. I'm saying the observation. I'm thinking today is for Thursday. I'm sorry. So you have one lunar observation today. You have another one next week, and you have another one the week after. So don't lose sight of these things. They take only a few minutes to go outside and monitor the moon and come back. Once you find that they're in good shape, you don't have to go back again. You don't find it, try to take several hours and go back again, or go in the morning and you're done with it. But you already know what to do. You already have spotted the moon from yesterday, because you're supposed to do a planning state from yesterday. So you know where the moon is going to be and what time and things like that. So you're going to your observation, document it, and you're done with it. Okay, sounds good?
Yes.
Very good. So let me share with you the screen, because we still have a unit which is of great importance to cover. And then we're going to talk about basically the next step. Okay, so the unit which is 35, which is part of this midterm, okay, which is really needed also to cover it. And it's basically the origins of the solar system, where this thing came from, okay? One of the things that we always repeat and say is that the sun is about 5 billion years, the solar system started forming then, and the Earth, for example, is about 4.5 billion years, so it forms a little later. And how do we know all of these things? Which is really a important question, a legitimate question, because somebody will question you and tell you, how do you know the universe is, the solar system is actually about 4.5 billion years ago? That's when it was born. So you should be able to answer that question with confidence. And the answer to it has to do with radioactive materials, okay? This is a known fact that radioactive materials will decay. They change. So you start with a material and it's going to change to something else. So the material you start with, the parent, and the daughter that forms out of that decay is the product of that operation. You might end up with two daughters or more, okay, in a single process. So depending on the process, you might end up with different things. Most materials, for the vast majority of the materials, they have this property, radioactivity. Now, some of them can take longer than others to decay, and others can take shorter times to decay. So how do we characterize that? We characterize it by what is known as a half-life. Meaning, if I have a certain quantity of an object, an element, I ask, how long does it take for me to lose half of it to a daughter or several daughters, okay? That is by definition the half-life. This is a constant, it doesn't change. Radioactivity by itself is a probabilistic event, meaning a single atom can decay now, tomorrow, the day after, a month from now, or 1 billion years from now, or 5 billion years from today. You can't tell for a single one of them how long it's going to take before it changes. But if you take the ensemble of all of the atoms inside the material, then that is deterministic. We know how long it's going to go before half of it is gone. That is a fact. It's not going to change. So this is one of its properties, basically, of radioactivity. Okay, this is basically something is not unique to radioactivity. There is all kinds of things. For example, temperature. When we talk about temperature, we're going to talk about that one down the road. Temperature is how fast the particles in the room are moving. Okay. If you take a single particle, it's moving and it's moving fast, but it's not going to create temperature on its own. If you take 5 of them, they're not going to create temperature. But you have to take the entire room made out of a huge number of them so that they collide with the walls, they collide with your skin, and if they are moving faster and faster, the temperature is getting hotter and hotter. If they slow down on average, then in this case, the room will cool down. So that's basically the temperature. A given particle may be moving faster than most of them, or a given particle may be moving slower than both of them, than all of them. But at the end of the day, it's just an average. Just the same thing was going on in here. The average is the only thing that matters. The temperature will be maintained, okay, at that point. Granted, some of them are moving faster and some of them are moving slower, but the end, it's a statistical event that is for sure gives you the average velocity, or the average velocity of all of the particles, the average kinetic energy of the particles moving in that room, or the agitation inside the solid. And that is basically what the temperature is. And that is actually a similar effect. These are called the emergent properties, like the temperature. It's not inherent in itself to the particle. It doesn't have a temperature itself. Same thing in this case. Radioactivity does not have an atom does not have a half-life. An atom can go radioactive now, or can wait several times the half-life before it goes radioactive. But an ensemble of them, they have a unique property, and that property is coming because of their collective behavior, okay? So that is something. Then we're going to talk about how the solar system came to be and try to answer those questions that were lingering from the last time, basically. Why all of the planets, or all of the objects in the solar system seem to be moving in the same direction? If it was really a random event that created the solar system, they should be moving every which way, okay? One of them is going this way, the other one is going this way, if it's really a random event. But no, there is a law that governs that, and it's the key word for that law is angular momentum. I know the word sounds kind of a big word, but it has to do with the spinning, how fast an object is spinning versus how much inertia it has. I mean, if you take the ballerina, I'm going to draw a ballerina, and if she has her hands closer to her body, she's moving faster than if she opens up her hands. Okay, in this case, she's going to slow down. So you're asking, did the ballerina gain already weight? No. Why did she slow down in here? Okay, did we put something on her head all of a sudden that she did not have before? No. The only way that this one slowed down is because of the distribution of mass. Initially, the mass for her arms were closer to her body. Now it's further away from her body, so she was going to slow down. I mean, if you don't believe me, let her bring her hands closer to her hands, and you will see that she's going to gain speed again, all of a sudden. Okay, nobody's pushing her, nobody's coming in there and making her spin faster and faster. And that is what is known as an angular momentum. So it has to do with how mass is distributed, how matter is distributed, matter distribution. This is exactly what happened to the solar system. You have a lot of scattered gas and dust from whatever explosions that was in the solar system, spanning light years, far greater what the current size of the solar system is. That's from earlier explosions that happened in the same region where the sun formed. Because of the force of gravity, they started to come closer and closer, okay? Lumped together, okay? So now, because of this lumping, it's as if she's bringing her hand closer. So things starts to move faster and faster. And the temperature in this case increased inside. This is the sun, actually. That's how the sun formed. And that's how the planets also formed. So as you bring things closer and closer, their speed increases more and more. And I just mentioned the fact that if you increase the speed, what you're actually increasing is the kinetic energy. And if the kinetic energy increases, guess what? The temperature also increases. That's exactly what happened in here in the case of the solar system. Well, there is another thing that you need to know about the angular momentum. It's not just a quantity that changes, but it's actually a vector. So it has to be conserved both in magnitude and in direction. The conservation in magnitude makes these things move faster and faster. So that is one thing. The conservation in the vector makes it flatten whatever. So the initial distribution was not flattened. It was every which way. But as you bring things moving faster and faster, it starts to flatten. And that's why from unit 34, we saw the solar system for the main part, at least the most massive objects in it, they're on the same plane. They're on the same flat surface, basically. The lighter objects, because they get knocked off here and there by the bigger ones and even by colliding with one another, so they go off track a little bit, and there is no harm in that because they are lighter anyway. But the objects that are in the flat solar system itself, they obey, all of them do, by the way, even the ones that get knocked off by conservation of the angular momentum, with the exception of those they get into later collisions, and that still has caused them to move in other directions. So this is basically what I'm describing, and here is the nebula theory and how the solar system came out to be, okay? And then when they condense, of course, it's like the differentiation in planets. The more dense materials, or at least they form in this case in this region, and then there is that frost line that is made mainly of lighter materials, mainly of water and actually solid water. It's ice then, and gas. Okay. And even basically, when the temperature gets so low at some regions, even the carbon dioxide also freezes. Okay. Like, for example, even on the surface of Mars, actually, there is the cycle of the carbon dioxide, which at some points it freezes on the surface and then evaporates, sublimates, because it doesn't go through the liquid form. So carbon dioxide goes from solid to liquid, similar to dry ice. I don't know if you guys have had experience with it or not. If you have dry ice, put it in a bucket of water because its temperature is getting hotter and hotter. So it evaporates immediately and forms those bubbles that you see in the dry ice, and so it goes gas. And then, okay, the process of differentiation actually explains exactly how the planets formed, because a planet, when it initially formed, has all kinds of matter in it. So it's more of a homogeneous distribution of matter. But then the denser materials will sink inside, and the lighter materials will come to the surface, again, because of how matter is going to settle down. And the cores form in this fashion made out of heavier elements. So this is in a nutshell, the unit for this that we're talking about. Again, the first idea here is radioactivity. The law that is governed by it is this expression, okay? I mean, it's a mouthful. So the fraction is 1/2, by definition, of T over the Greek letter tau. So if you're not familiar with this one, this is the Greek letter tau, okay? Tau, T-A-U. U, I don't mean W. U, okay? The Greek letter tau. So this is the half-life. Tau is the half-life. Okay, what I mean by that, okay? If the time that has lapsed from the beginning, so it starts with a certain amount of matter, all of this is it. After tau time, only half of it is left. The other half has changed to something else, okay? Like in the case in here of potassium, it could change to argon and calcium in the same time, with calcium being the main daughter and argon is a secondary daughter, but they're still both byproducts of this decay. Let's start with 100,000 atoms of potassium, for example, or particles of potassium. I will end up with only 50,000 times after a billion 0.28 years. It's a long time, okay? Then in the same time, I have formed 45,000 particles of calcium and 5,000 particles of argon. This is after 1.28 billion years. After another 1.28 billion years, half of the 500,000 is going to be changed to calcium and argon in the same proportions, basically. So the first half stays from the initial 50,000, I will be left with 25,000. So in here, 1.28 billion years passed, and there is another 1.28 billion years. So after 3.65 billion years. Okay, after that, only 25,000 particles of potassium are left, meaning 75,000 already have changed. Okay, so the 75, they go in the same proportions of the initial distribution, so they stay the same order. So in other words, 65,000 and a half, 67,000 and a half is calcium, and 7,500 and a half is argon. If you add these two, they will give you 75,000. So this is the daughters now, 75,000, and the potassium is only 25,000. To add up back to the original quantity in here, okay? If I wait another 1.28 billion years, so you're thinking this one is 4, this one is 8, and this one is what, 4? After almost 5 billion years, this is how much potassium will be left with, 12,500, but now there is an abundance of calcium and argon. Okay. Initially, after the first process, still potassium is still very abundant after 1.28 billion years in this sample. But the quantity flip actually, according to, for this one, after the second half-life. Okay. The third half-life, basically, the parent is hardly there. Okay. Now, after add to it another one, so it's going to be 1.28. So this is 12, and this is 11. And this is 5.12 billion years. This is how much basically potassium, hardly left any, but mainly it's calcium, because calcium is being made a lot, and argon is this is how much. Actually, there's more argon now than even potassium that we started with. So the point being in here, this is actually a good way of keeping tab of where things are. So if you're given a sample, by the way, the samples from Earth are a little bit, how should I say, tainted, okay, because there are other processes on Earth. because of its geology. But the asteroids, for example, that hit the Earth and become meteorites, so the meteorites in this case are actually very, very useful thing to study the history of the solar system. As a matter of fact, even the rocks on the moon are actually good to study the history of the solar system, trying to see exactly what happened to the solar system initially and where it came from and so on and so forth. The asteroids actually that are still in orbiting the sun in the asteroid belt, they're actually even better because they are raw materials. They tell exactly the history of the solar system, when it was formed and all of that. So if you take a sample and you determine the ratio of the parent to the daughter, you're going to be able to tell how old it is. So this is basically visualization of before. So this is actually after a half year, and this is the proportions. Half of it is gone, okay? And this is, did I give you the wrong information? I'm sorry. Oh, the argon to potassium ratio. Yeah, the daughter to daughter ratio. Those are the numbers, daughter to daughter ratio. Okay, and that's how they're increasing also because you're losing. I'm sorry, argon to potassium ratio, daughter to parent ratio. What am I talking? 5,000 over 50,000 is 0.1 or 10%. 7,500 over 2,500 is 30%, and so on and so forth. So that's what that representation is. But the point being in here is, initially, I only have potassium. After a half-life, I still have basically 50-50. So I have a lot of calcium and I have a little of argon. And if I add them up, they add up to exactly the same amount of potassium. And later on, I lost a lot of my potassium, but now I gained a little bit more argon, and then the calcium now is dominant in the sample. At some point, the daughter, which is in this case the argon, and the parent, they are very close from each other. They are not exactly equal, but they almost have the same quantity. But there is another daughter now that is dominating the whole sample, namely in this case calcium. And then at the end of the process in here, I have more daughter, in this case argon, and I have more daughter in this case, which is calcium, than actually what I started with, which is a potassium. So based on this, I can determine the age of the whole solar system, or at least the sample. All I have to do is find these ratios: daughter to parents and daughter to parents. And from here, I can conclude how old the sample is. This is a very, very powerful technique. This is exactly what was used to determine the age of the solar system. So the solar system is not 6,000 years old, okay? Whoever says that is not, at least doesn't know anything about science, okay? So based on what we learned, again, planets must revolve around the sun more or less in the same plane. So we need to understand where that is coming from. So the planets are on the same plane here. Okay, the big objects, they're on the same plane. Planets must rotate about their axis in the same direction. So they're all moving in the same direction. Okay. And also on their own axis around the same direction. I mean, granted, there is a tilt of 23.5 degrees for Earth, and there is 25 degrees for Mars, and granted, there is about 3 degrees for Jupiter, and so on and so forth. There are exceptions from Unit 34, big time. Venus is almost 180 degrees. And Uranus has a tilt of slightly more than 90 degrees. Okay, so those are tilted big time. For Venus, it's upside down, really. So if everybody is pointing up, Venus is going down. For all practical purposes, this is 180 degrees. This guy, Uranus, is not up, not down. It's actually completely on its side. But those are the exceptions. Again, the exceptions should have explanations on their own. What happened to them after they formed like everybody else did? That is the question that you need to ask about the exceptions. So they don't make the rule. You just focus on everybody else. Once you have an explanation for everybody else, then you're going to discuss the exceptions, basically, try to find what happened in that. And then the structure also, the inside is more rocky and the outer ones are made up of basically our ice, or, okay? gas and things like that. So again, the nebula theory explains that one. So in the region where Earth is and the sun is and everything else, a region of about 3 light years that has dust and gas, remnants of whatever happened before, or some other stuff that happened in the same region, basically supernova or supernovae, more than one that happened in this region, and that fed the formation of the sun. As a matter of fact, the region where the sun formed other stars also, but they diverged. They moved away from each other. So there are other stars also formed out of that remnant. But it was basically 3 light years. It's a huge region. You cannot even imagine how big it is. It's almost a distance from here to the nearest star, which is Proxima Centauri. Okay. So it's a big distance, big span of space that has a lot of dust. And that, the force of gravity started to bring it closer and closer until today, or at least when this, just before the Big Bang, this is how big it is. It was about 200 astronomical units. Just to give you an idea, a light year, and I mentioned that before, a light year is how long or how far the light will travel in 1 year. Remember, in 1 second, light will do 300,000 kilometers. This is in 1 second, but I'm not interested in 1 second. I want to know in 1 year. 1 year is actually 365 days, and a day is 24 hours, and an hour is basically 60 minutes, and a minute is 60 seconds. So I have to take these numbers and multiply them by 300,000 kilometers. So 300,000 times, to find how many kilometers that is, it's a huge number, times 365 times 24 and times 60 times 60. I know this is what the light year is in kilometers. Okay. So I know the book has a number for you that you could remember, but it's worth actually knowing what that number is. So let me stop sharing and let me try to pull a calculator in here. It's useful to do this one at least on your own. Okay, so let me share the calculator that I just made. So what I have in here, I said light does 300, I need to write 300,000, okay, kilometers per second. But I'm not interested in second, I want to know it in a year. A year is 365, so I multiply by 365. So this is how many I have in 300 in days, basically. And then I want to know a day is 24 hours, so I'm going to multiply this one by 24. And I also need to multiply this one by, what happened? Okay, so this is the number. Okay, so I need to multiply this one by, okay, man. Okay, never mind. I need to restart again. So let me delete that. Okay, I lost track of my numbers. So I have 300,000 kilometers. That is basically per second. Multiply that by 365. Multiply that by 24 hours. Multiply that by an hour has 60 minutes. So multiply that by 60 and multiply that by another 60 because I just got it in minutes. So we really need to multiply it another one to get how many seconds there are. It's 9, and then you can count how many decimal points there are. There is 1, 3 of them in here. 3 of them, that's 6. That's already a million. So this is 1,000, million, a billion, and this is trillion. Kilometers. Okay. This is a light year. But you're not talking about 1 light year, you have 3 light years. So I'm going to multiply this one by 3. So this is the extent of which, okay? So you're wondering how many astronomical units that is, because an astronomical unit is 150 million kilometers, and this number is 28 trillion, whatever that is. How many zeros again? You have 1, 2, 3, 4, 12 zeros. Yes, 28 trillion kilometers, okay? So if I divide that number by 150 million kilometers, this is 150,000. I need to have 150 million. So this is 150 million. This is astronomical unit. So the answer I'm going to get to you now is how big was the solar system in terms of astronomical units. So it was 189,000 and shrunk down to 200. So basically it was 200,000 and shrunk down to 200. So it shrunk by a factor of 1,000. So let me go back into the screen where I was before. So this size from here to here is 1,000 times bigger than this size. So it shrunk by 1,000 times. Okay, obviously, what happened in here? In this case, the key word in here is a conservation of angular momentum. In other words, nobody was spinning the solar system or retaining it from spinning. Okay. Nobody did that. So if you're, for example, have the bathtub, for example, full of water and you're enjoying your bath, and then all of a sudden you would want to get rid of the water. So what you do in this case, you remove the plug. Once you remove the plug, the water starts to spin inward, going into the drain. Okay. Before it was not spinning. It's not like you are actually steering the water, trying to help it to go. No, nobody does that. It does its own. Okay, just the motion as it triggers, it's going to start to spin inward, going into the drain. This is similar fashion. The matter was very far away, and as it gets closer, it starts to spin. So what is that? That is a conservation of an angular momentum. So if you have a rubber ducky, for example, you can keep tab of the motion of the water. All you have to do is put it on the surface of the water, and you will see that the rubber ducky starts to move. When it's far away, it's moving slow, but as it gets closer from the sink, it's going to move faster and faster and faster. So that is exactly what happened to the solar system. And that thing there is called the angular momentum, okay? That causes it to move faster near the sink and near the drain, I should say, and slower far away from it. That is the angular momentum for you guys, okay? Now, as I said before, the angular momentum is not a scalar. It's not like the temperature that is basically it's not like the temperature, which is a fixed number. I mean, you move around anywhere in your room, the temperature doesn't change direction, doesn't change value just because you look in the opposite direction. So it's not a direction value, okay? It may change value because you move from one area to the area, but when you look left or you look right, it's not going to change. It's the same number in that place. So it's not a vector, it's a scalar, it's a number. But the angular momentum is a vector, actually. It has a preferred direction, okay? This is why bathrooms in the northern hemisphere spin in direction other than those in the southern hemisphere, because again, they want to conserve angular momentum in one direction, and the Earth is spinning in the opposite direction. This is actually why hurricanes form in the northern hemisphere in their counterclockwise motion, whereas in the southern hemisphere they form into the clockwise motion. Again, it has to do with that, and that's the same thing what causes actually the big red spot on Jupiter and all of those hurricanes on the planets. So it's the same thing, albeit in that case, I'm including another force that I'm not mentioning in here, and that is the Coriolis force, okay? But the point being in here is this has to do with the conservation of angular momentum. And angular momentum is a vector, so the whole thing starts to flatten. Just like when you take a dough, for example, which has this shape, and then you start to spin it, it's going to start to flatten and flatten. If you're in the business of making a pizza, for example, you know that out of experience, okay? There is another thing in here. As gas cools, it expands, in this case, and goes in all the directions, and the opposite is true, okay? The opposite is true. So this has to do with the condensation and how the process works in this case too. So this gives us an indication based on the condensation temperature and where they condense. That's why you have hydrogen in this case, requires very low temperatures to condense, to become liquid basically, okay, to liquefy it. And helium actually goes all the way to 3 Kelvin. Helium never solidifies because there is another state that appears in there. Carbon requires higher temperature. Oxygen, depending on if it's a silicate or it's a gas, neon, it's even lower temperatures, and iron requires much higher temperatures for it to condense. So in this case, it condenses at higher temperatures, meaning it becomes solid, actually, liquefies, and then it becomes solid at even lower temperatures. So this explains basically the composition of the different materials. For example, if you look at them in terms of the Earth, because the Earth temperature is a lot less than 1400 Kelvin right now. So iron is actually a good major component. Same thing with silicon. Remember, silicates is where the oxygen and silicon combine. Both of these two temperatures are the same, except that oxygen can exist also in a gas form, and you can liquefy it. So that you guys understand the scale of temperatures in here that we're using, because we're not really accustomed to these things. So when somebody tells you 300 Kelvin, that is actually room temperature. That is about 23 degrees Celsius, which is about what, 75 or 80 degree, no, about 75 probably degree Fahrenheit, okay? So this is something that you need to know. So when somebody tells you it's 180 Kelvin, this temperature is way below the 0 degree Kelvin, because 273 Kelvin is equivalent to 0 degrees Celsius or 32 degrees Fahrenheit, okay? That is where the water freezes. So water freezes at 0 degrees Celsius or 32 degrees Fahrenheit, okay? That is super cold, where it becomes frozen. In Kelvin scale, that's 270 degree Kelvin, 273 Kelvin. I made a mistake. We never say degree Kelvin, by the way. It's and people sometimes say it, and you might hear me say it, and that's a mistake. We really should say call it Kelvin with no degree in it. Okay, so that's a mistake. You always have to say degree, and you have to address these things with the little zero on top of them when you talk about those, because these are the scales that they use. This is more like a unit rather than a scale. Now, when I'm talking about 180 Kelvin, this is less than 273, which means it's less than 0 degrees Celsius, which means it's less than 32 degrees Fahrenheit. So 273 is actually, make 273, deduct from it 180. So in this case is what? Or actually 180, deduct from it. Oh, it's that. Yes, correct. Never mind. Okay, here is the scale. Here is a 0 degrees Celsius, correct? And here is where the Fahrenheit is. So this is the 0 Kelvin. So anytime I give you the temperature in degrees Celsius, you add to it 273, okay? So in this case, I really should subtract 283 just to get it in Celsius. So it's 180 minus 273, and that is going to be 7. 18 minus 8, that's 0. So, and this is going to be what? Negative, what am I doing in here? Yeah, I think it's 273 minus 8. Anyway, the point is going to be a very low number, okay? And it's going to be a negative number. So it's going to be 39, it's negative 37, 93 degrees Celsius. That's what I'm trying to say in here, that this is a super cold temperature, okay? Extremely cold temperature, okay? It's below freezing. So when you see a temperature of 180 Kelvin, you might be thinking that this is a high enough temperature, but it's not. It's way below the freezing temperature of water. That is the point I'm trying to argue in here. So the Kelvin in here is a convenience scale. Kelvin can never be negative though, because the maximum it can be is basically 0 in this case, which is here, okay? So that's the maximum temperature you can have in here. Anyway, I hope I didn't confuse you enough. If you did, I'm sorry. The point I'm trying to argue in here is this temperature is extremely cold. This one is even ridiculously cold. This is negative 270 degrees Celsius. Okay, it's almost the absolute 0, okay? Because 3 Kelvin is just barely above 0 Kelvin. And then 80 Kelvin also for carbon is super, super cold, okay? And carbon in here, it's methane. That's what they mean by it. And this is nitrogen in this chemical compound. So the point being in here, this Earth, because of its temperature, doesn't have these proportions. However, because the sun has is mainly ionized, it has this this composition. This is from when the sun formed, actually. This is all the stars, they have this ratio for their hydrogen to oxygen, I'm sorry, to nitrogen, to helium composition. So you have hydrogen about 75% and helium about 25%. For the case of the sun, it's slightly less than 70%, 75%, so it's 70%, 71% to be more closer. And then the helium is slightly more than 25%. Man, they're making a lot of noise. I'm sorry, guys, about this, okay? Anyway, the point being in here is this is the composition of the, the sun, and that indicates that the sun really was not formed when the universe formed. Because this composition came from after the Big Bang. After 300,000 years of the Big Bang, the stars that forms immediately have these ratios: 75% hydrogen, 25% helium. The sun has less hydrogen and more helium in it, meaning that it was not formed initially. So this is it was not formed when the universe formed. As a matter of fact, the universe formed and almost 8 billion years later when the sun formed. So the sun is a new star, relatively speaking, compared to the universe, a lot newer than the universe, okay? So universe is much, much older than the sun, and that makes sense. Because if the whole is younger than the part, that doesn't make sense, okay? But the whole in this case, the universe, which is 13 billion years, 13.7 billion years, is older than its components. One of them is the sun, okay? And this is an indication of why that is so. What about this noise? Okay. Anyway, the point being in here is this is also explains the composition of the different objects in here. Somewhere around this region, actually around this region, is the frost line. Anything above this one is where water and basically carbon, methane in this case, they can exist in other forms than gas. As a matter of fact, they start to liquefy at some point in here. This is for ammonia, and this is for methane, okay? So they start to condense further down. Water condenses just around Jupiter. You're wondering now, what happened to Europa, for example, the moon Europa, which is moon of Jupiter, because now if you heard about it, if you didn't hear about it, you can hear about it, that it has a thick ice crust, and then there is oceans in here of water, and that water is in liquid form. Not only that, but it's actually salt water, okay? So which could harbor life on it. So that's really, it has more water on Europa than actually Earth does. So the question is, why is it has liquid in this case? And you're telling me in here that it condenses. Well, the answer to this one is simple, because you have this cover, this protective layer from ice that protects basically the inner parts, and that makes it where the liquid part is protected in there. Okay, so that's basically, I mean, one of the properties of water, and this is actually a very good property of water, is that water freezes from the surface down. Okay, so if you go on a lake, for example, in the Midwest, like Minnesota or something, and you go to a lake and you will find a solid sheet of basically ice, the underneath of it is liquid still, because it starts to solidify from the top and the bottom. Unlike other materials that they go from inside out, this one is from top to bottom, from the surface down. And this is actually a good thing. Otherwise, the fish that makes this home will freeze to death underneath, okay? And this is true also for Europa in this case too, okay? So it's frozen from the outside, and actually not only Europa, other moons also, like Callisto and Ganymede also, and some other moons also from the outer moons, they have these similar properties, where they have a liquid inside and the water inside, and they have this protective layer in here, similar to the lakes that we have on Earth. Because if water does it in the other way around, where it freezes from the bottom up, then in this case, the minute the temperature starts to drop, it's going to freeze. So the fish, they will be forced to go up. And then as it freezes down, they will have no room, and then they will freeze to death, okay? So this is actually a good property of water. And that's what's going on actually here. Yes, water condenses and becomes liquid and then actually solidifies, and then it becomes solid, icy basically structures, and that is how the different objects in the solar system are. Actually, they have this composition. Okay. Again, as the sun formed and it was forming, other planets starts to form, matter starts to condense in a similar fashion and starts to basically become bigger and bigger. The first object to start to coalesce in here in these lumps around the sun were actually Jupiter. And the reason why we know that is because Jupiter is the biggest object in here in the solar system after the sun. So it must have started early on compared to other planets. And then the next one and so on and so forth. Okay, so this is how they are. And so the rock starts to coalesce. And in the case of the outer planets, they attracted gases in them, namely hydrogen and helium, which was the most abundant element in the area where the sun formed. But because of their sheer gravity, can you guys hear me?
Yes.
Okay, sorry about that. I don't know. Sometimes it does this. It's kind of a... Anyway, so I was talking about the I'll share the screen. Basically how the planets formed, okay? And they form in different regions depending on they are and how they start. And that is basically the theory that we have into how the solar system came out to be. Obviously, when the solar system formed, it had a lot of material in it. So it immediately led to different kind of collisions. And one of the indicators of those collisions, if you look at the moon, you will see a lot of craters on its surface. And actually, this is not unique to the moon. If you look at Mercury, if you look at the moons of Jupiter, for example, anywhere in the solar system where there is not much geology going on in the surface, basically. And like, for example, the surface of Mars or the surface of Earth or the surface of Venus or even that of Jupiter or anything like that, you have weathering, you have actually different phenomena, you have actually atmosphere, and you have water cycles and things like that, that causes the surface to rejuvenate itself and renew itself. So you lose that thing. Other than that, this process left a lot of materials in the solar system, some of them small, some of them big, and they started colliding, okay? And those collisions are the impact that you see, at least when you look at the moon. That is actually the telltale of that sign, of that thing that is going on. So part of the process also is the process of differentiation, because when the planets form, like for example, the case of the Earth when it was formed, it has all kinds of materials in it. So it was more or less the distribution is uniform in it, okay? But then because of the heat, the original heat, so the material was more or less liquid. So in this case, what happened was the denser materials will sink in, like iron and nickel, and form the core. And the lighter materials, the silicates, they move up and form the mantle that we know, at least for the case of the Earth. So this is fully differentiated, similar to what happened in this case in here, okay? So the chips of the ice cream will fall down, and then the liquid, and so this is basically you have a similar structure in here, how materials also differentiate. Okay, so this is something that's going to tell us basically how the planets look like. At least for the case of the Earth, we know that for a fact. And now we have probes actually on Mars to study Mars quakes. Again, the late bombardment state is that actually when the impact started to hit the planet, and this lasted for a long time. And on the case of the moon, for example, it's marked with these impacts, and they came in with a lot of, and they came in all directions. Okay, and you can tell their age by two types basically of impacts, two types of craters in this case. For the case of the moon, you have the ones that are older, and the one that came on top of them, those are younger. So you could tell the age or the history of the solar system just also by studying these things, provided you had a surface that is not changing, unlike the surface of the Earth, which is now hardly you can find a crater somewhere. You have to go probably to Arizona to find the next biggest crater nearby, which is Arizona crater, or is it meteor crater near Flagstaff. Okay, so that's basically something that you can guys go and experience. And this is something that happened actually to the solar system, not just the moon. All of the objects in the solar system were subject to, including, by the way, the sun. So the planets, as they were moving and basically trying to sit in their positions, they were shifting. At least the biggest one was doing that, was Jupiter, this smaller object, in and out. Okay, some of them were thrown all the way to the sun. Others, they were thrown against the planets, the inner planets. And some of them were ejected completely out of the solar system, and others basically were impacted the big objects in here. All of these planets that you see them in their current positions, they have been shifting in and out, okay, especially the big ones, and they move things in and out. So it's really something that is evolving. Has it stopped? No, the whole process is an ongoing process. So it's really not the whole solar system is actually shifting still. Okay, it's on the geological level in here, or at least the age of the solar system. This is an extremely slow process. Then you have atmospheres that form. Two ways of forming atmospheres, either by collisions or impacts. So when the matter hits the ground, it's going to obliterate itself, and basically the outcome is going to go and evaporate and become volatile. For the case of the Earth, that's how it received most of its water. Okay. And that's how we believe a lot of comets basically hit the Earth, and basically the water that they were carrying basically evaporated and then rained down again to form all of the oceans, or through outgassing, namely volcanoes, really the main culprit in this case, forming gases, all kinds of materials that are released in the atmosphere. Some planets are different than others in terms of their size, and they will retain those gases longer than others. Okay. For the case of Jupiter, it's supermassive. It's retaining most of its gas, basically. Yes, there is an escape of gas, but it's hardly anything compared to the mass of Jupiter. For the case of the Earth, also, it's a similar fashion. Earth is losing the lighter gases, because remember, I mentioned the analogy earlier with the temperature, and you have the fact that some materials are moving faster than others to indicate the temperature. So on average, they're moving with the average temperature, but some of them are moving super fast and others are moving super slow. The ones that are moving super fast, they will move so fast that they will escape the pull of the Earth. There is something called the escape velocity, which is, for the case of the Earth, is 11.2 kilometers per second. Any object that reaches this speed is going to escape the Earth. That's how rockets actually are basically built, so that if you want them to basically send them outside of the Earth, you need to reach the speed somehow. For the case of the gases, on average, they are moving with the speed. Some of them are moving faster than others. Some of them are moving faster than this speed, so they would escape. Okay, this is an average quantity. So this is always happening for the case of the Earth. So what the Earth is doing, it's doing an outgassing. It has volcanoes, it has all kinds of things that is replenishing its atmosphere on a continuous basis. Okay. For the case of Jupiter, for the case of Venus, for example, what's going on in this case, it's replacing more than it's actually losing. So Venus has a very, very thick atmosphere in its thing. So it's actually a lot thicker than that of the Earth. For the case of Mars, it's a lot smaller than the Earth. So it did not have enough, first of all, geology on its surface because it's a lot smaller. So geology on it stopped a long time ago. So it stopped basically from replenishing its atmosphere. but it has lower gravity anyway. So the escape velocity on Mars is a lot less than that of the Earth. Combined with the fact that you don't have enough replacement anyway, so that's why most of the atmosphere is gone. If you guys remember from that movie, what is it, The Martian, with Matt Damon? At some point, he was stuck on the planet and he wanted to reach basically his rescuers. So he had to compute he had to know the escape velocity, and he had to do all kinds of things. And even at the end, he came short of that. So at the end, in the movie, if you didn't see the movie, I'm ruining it for you. I'm sorry, but he had to puncture his suit and put it in hand so that to regain that extra push to reach his rescuers and basically be rescued. So again, it has to do with escape velocity. So again, objects retain their atmosphere that they have formed, they have earned, either through outgassing or collisions. But that retention depends on their mass. For the case of the Earth and Venus, they are big enough to retain it. For the case of Mercury and Mars, especially Mercury is a lot smaller than the Earth, and that of the even smaller than Mars. So it lost all of its atmosphere. Same thing is true for the Moon, by the way. The Moon also had an atmosphere probably in the beginning because it had geology too. All of the objects were hot to basically form all of these things. And they were under subject of also collisions, impacts. So they had atmosphere, but they couldn't retain their atmosphere for the same reasons that they don't have enough gravity to retain it, okay? And they did not continue with the process of making more and more of those, replacing basically those gases long enough to keep their atmospheres, okay? So again, these are the units for this week, okay? We discussed unit 34 last time. This is unit 35, okay? I am hoping that you guys will go through the review again. It's by far the most important one. If you guys run into a difficulty with the homework, I would be more than happy to discuss it with any one of you guys anytime, whether this weekend or next weekend or whenever you guys feel like it. Again, just as a reminder, we don't have a live session this coming Wednesday, but we have one on Monday. We still are meeting on Monday on the same time. Sounds good?
Yes, thank you.
Okay, thank you guys. I'll see you guys next time. Lab is never canceled, okay? We always have lab for those sitting in the lab. Okay, bye.